Hi everyone, welcome to today's ARGA webinar. Let everyone join and get settled in. Hey guys, how you doing?
Hi, Anna.
How's things? All right, just so people know, we are recording. So we do record. We won't record the waffle at the start, but we will. This will be put on YouTube in terms of Richard's talk, and you'll be able to check it out on the ARGA YouTube page. We'll give people a couple more minutes to come along. We'll get started in a couple of minutes. Yeah, hope everyone's keeping warm today, or whichever part of Australia or the world you're part of. All right. Hey, Mario.
Hi, quite cold here in Perth.
Ah, it
Mm.
looks sunny still though.
Uh, yeah, well, a bit cloudy, but not. It's not gonna rain apparently.
Yeah, you guys have got a lot of rain lately.
Yes, yes,
Yeah,
yes. For
yeah,
several days in a row.
yeah. Yeah, we finally got some rain, so that was nice.
Mm.
Cool.
And there in Adelaide, how is
Yeah,
it going?
it's nice today. We had a bit of rain this morning and it's cleared up, so it's pretty good. I like the big puff clouds that come across and that sort of coastal weather. It's nice. Yeah, that's what I like about Adelaide. But
Right,
we definitely
right,
got hammered last week. Yeah.
great.
It was cold enough last week. It's nice to have a break. Yeah. All right. Cool. All right. I'm going to get started. Welcome, everyone. This is the July webinar for the Australian Regolith Geoscientists Alliance. So I'd just like to acknowledge that I'm meeting you all here on Ghana country, and I know ARGA members and guests are coming from all across Australia and beyond. So we just like to acknowledge the traditional custodians of the land, the First Nations people of Australia and elsewhere, and their ongoing connection to the past, present, and future. Um, we today have a really special guest, Dr. Richard Lilly from the University of Adelaide and NExUS, the National Exploration Undercover School. It's going to be a really great webinar, and what we are hoping is that we can get another really great webinar set up for the next few months as well. So if you or anyone else you know would like to present, please do get in touch with us, myself or Leah, or email secretary@regolith.org.au. We'd love to have you present. We are after all types of talks because, as you know, regular science can cover quite a lot of things. Right. I don't know if we do have one set up for the next month, so keep posted, keep checking out LinkedIn. I know lots of people do find our talks that way, and we'll keep sharing it through our community and our group. Today, I'm really excited that Richard is talking about exploration for gossans and secondary minerals in the regolith. So I believe this is part of the course that you do as well, Richard. Is that right?
Yeah, we've got a course on Monday actually. So if anything in here sparks interest, I can see Aditi and Ben who are already registered for that course on Monday. But it's still time to register. I'll put a slide in about that. So if this is a topic that is of interest to people, we have a whole 1 day course on Monday about this, and this is just a bit of a highlights package of some of those things. But as said earlier, I know I'm not going too much into depth today. This is a bit of a sort of a bit of an overview and some pretty pictures of rocks, really.
Excellent. Oh, well, thank you. Well, without further ado, I don't have like a formal introduction for Richard, but I'm sure he's going to tell you about all the amazing work he has done all around Australia and elsewhere. Richard, most people will know that has a huge amount of exploration and mining experience, and I think it's going to be really exciting to hear about some of the work he's done in the past and some of the research that he has been leading. And so I'll pass over to Richard. So thank you very much for presenting today, and the floor is yours.
Cool. Thanks very much, Anna. Thanks, Leah, as well for the invite to take part today. Always happy to chat. Can you just confirm, Anna, that you can see me and hear me and everything's good?
Can see and can hear. Thank you
Excellent,
very
thank you.
much.
So I guess today's talk is about exploration with gossans and secondary minerals. As I mentioned, I could probably we do have a 1 day workshop on this on Monday, and this is a topic that I think is probably one of the things that really got me into exploration. Hence this first slide. Why do I love exploration? Was looking for things, isn't it? In exploring, trying to understand what we're doing. And for me personally, one of one of the first things that got me involved in exploration was my summer vacation program in North Sweden with Rio Tinto back in 1999, which is a long time ago now. But it was wonderful. It was a summer of mosquitoes and the sun never went below the horizon sort of thing, and really doing proper exploration. And I think at the time there, jumping forwards, the rocks here are very, very fresh. There's not much regolith up in northern Sweden. We had a lot of till that was put down maybe a couple of thousand years ago at the most, but there weren't a great deal of secondary minerals around, and it wasn't, I was looking at fresh biotite, fresh amphibole, things like that. So coming from that first experience to my sort of work in Australia has been really interesting. It's been a fairly steep learning curve, but this certainly got me very much in love with exploration. And I did get a bit of a crush on geochemistry because my honours project was based on some of the till sampling that we did up here. Moving forward to Australia, some of the beautiful rocks that you can find or minerals that you can find above particularly copper deposits. That's been my experience. I worked up in Mount Isa between 2007 and 2015, and then subsequently I've been going up there a couple of times a year since then. And people can be people can be a bit dismissive about, we found all the deposits poking out the ground, but around Cloncurry, this sort of show of copper, the kind of the prospecting, the secondary minerals are everywhere. And very, very few of the occurrences have been drilled under. There must be thousands of Gossans and secondary mineral shows around just Cloncurry, and I'd say probably 1 in 10 has been drilled under. So I think there's definitely still potential, and recognition of these minerals is very important. Not only are they pretty, not only as a geologist will you fill your bag with them and take them back and put them all on your desk. My desk was weighted down a huge amount, but they tell you a lot about what's going on. This, for example, this is chrysocolla from Mount Glorious, a few K outside Cloncurry to the west, and chrysocolla is a copper silicate. So we know from just this mineral that there's copper there and there's silica. And actually, there's not a huge amount of silica in IOCG systems, which are the typical systems around Cloncurry. So the fact we have chrysocolla is, slightly unusual. What's it linked to? Obviously, we can see big lumps of white here. There was, quite a lot of silica in the Mount Glorious system, but it's, that is all part of the story. You can also see here these nice little roundels of malachite forming, which is a more of a carbonate mineral. And obviously that's forming where the copper-rich groundwaters have not got access to the silica because it's already coated in chrysocolla. So immediately, just from looking at these minerals, we can work out a little bit about what's going on. This is from Lorena, which is a gold mine just outside Cloncurry. Obviously, we've got the very, very vibrant azurite here. We've got some more chrysocolla, so we know we've got copper, we know we've got silica. There's touches of this darker green, which could be malachite, most likely malachite. But then we come over here, and let's see if I can just zoom in a little bit, just onto this little bit here. That green's a bit different, isn't it? And I remember I picked up this sample and just thought that was malachite, didn't really think twice about it. But you see there's a little bit of botryoidal stuff there, which actually I've never noticed before. A little bit of botryoidal green stuff. We follow down here, there's a kind of greeny yellow, and you think, well, actually, what is that? That's a bit different. And over here we've got this dark mineral, this black mineral, which traditionally I always assume was manganese, but seeing as we're in a mine that's got copper, it's probably tenorite, which is a black copper oxide. And actually, this green mineral turns out to be conichalcite, which is a copper arsenic mineral. Typically forms these botryoidal kind of masses. So just in this one sample, we've got 1, 2, 3, 4, 5 different minerals at least, not including the white mineral here, which is probably quartz or calcite. Who knows? I can't actually remember what that was. But this one hand sample is telling us an awful lot about what we're looking at. And the Lorena system is essentially an arsenopyrite vein full of gold and a bit of copper. So the fact we have conichalcite there is telling us that we have arsenic. So these minerals we're finding on the surface, minerals that prospectors have found for hundreds of years, are telling us important clues about what's happening in the original ore assemblage below. So they are cool and they sit on your desk nicely, but they're also very important indicators of what's going on. And an arsenic-rich system in Cloncurry is quite rare, and particularly a gold arsenic system. So it is relevant. So fast forward from my Sweden experience to getting my dream job in Mount Isa in 2007, coming over from the UK, thinking I was going to be scrambling over beautiful minerals every day. But in exploration, you don't always get the option of choosing your tenement area. And this was my first tenement area that I was sort of put in, had my sort of project running on. And this was called Silliman, and it was about 50k south of Tajara. So it was pretty much in the middle of nowhere. and there were bugger all rocks there, which was a little bit disappointing. I remember parking up and being a little bit confused that, I'm coming mapping here for 2 weeks, where are the rocks? As it was, I'm literally taking this photo standing on one of the outcrops. I still have that a piece from that on my shelf, actually, my first bit of desk sampling. And there weren't many rocks around. And we did some stream sediments, we did some soils, but there wasn't a huge amount to map. However, the one or two small outcrops that we did have, these hills were outside of our tenement area, and this was essentially the one hill in the tenement that had outcrop. I did notice coming from the UK that the vegetation was really different. And you noticed it as well when you start walking up the hill through spinifex. And if anyone has done a few days walking through spinifex, you'll know what I mean. Nice spiky grass. But spinifex has got it's a very sharp grass for anyone not in Australia, and it's sharp because the point's got silica in it. And the silica is, oh, excuse me, so I just clicked the wrong button. The silica basically needs, the grass needs silica. And so spinifex will tend to grow on a source of rock which has silica there. We also had, where are we? Let's go. We had an fairly obvious sort of topographic demarcation between the Gidgean lancewood on the alluvial plain and our spinifex, and then this turpentine scrub, which again, anyone who's worked around Cloncurry or Mount Isa knows very well about. It's a sort of acacia sort of scrub, I think. Anyway, it's very sorry, it's a form of wattle, hard to walk through. But anyway, I was just getting used to noting that these vegetation anomalies are particularly clear in these sort of arid, semi-arid conditions. Growing up in the UK, everything's covered in fields. You don't necessarily see a great vegetation variation. And so it's something I started to take note of. Then there was a particularly, probably on the same day I took that photograph, Erwin, our fieldy here, we walked to the top of the hill, and the only bit of shale, we were interested in this particular tenement because there was a report of an outcrop of a shale which was linked to the same shale that the Urquhart shale that hosts Mount Isa was. This was the only outcrop of shale on the whole of that tenement. And it was the only place on the whole of that tenement that this brown grass grew. And I thought, hang on a minute, why does this grass only grow on the shale outcrops? And I just thought that was really weird. I'd never noticed, I'd never seen that before. And this is where my sort of interest and sort of passion, I guess, for geobotany came in, because soon after that I was working on tenements that had a whole bunch of copper outcrops, and we were getting all this copper grass growing everywhere. Or more to the point, this is the Dugald River deposit just outside Cloncurry. Dugald River is a predominantly zinc, lead, silver deposit, but it also has appreciable copper. And the surface outcrop of the beds which dip in at about sort of 70 odd degrees that you can see outcropping here. This is the surface outcrop of the ore zone. And you can see it's monoculture almost. There you don't get the eucalyptus growing, you don't get the turpentine scrub growing, but you get a lot of this grass. And I remember thinking it's a bit weird. Why is only this grass growing on the outcrop? And when we did soils over the top of this outcrop, it's between 500 and 2000 ppm zinc and over 1000 ppm copper. And jumping forward a little bit, the plants here, this grass that is generally known a bit as copper grass around Cloncurry, it's a metal excluder. So it's developed within its evolution, it's developed a way of excluding these high concentrations of metal, which are poisonous to other plants. So it will inhibit plants from growing. The copper grass is clever. It has its own supply of fungus in its roots, so it doesn't need the fungus growing in the soil, because of course copper, anyone who wears copper bangles or knows people who wear copper bangles, the reason that's a bit of a historic thing is because copper is of course a good fungicide. That's why we dip wooden poles in it, and all the wood in Bunnings is green because it's been dipped in copper sulfate to stop bacteria, to stop fungus, from rotting it. So plants can't grow because there's no fungus in the soil to give them nutrients. However, this grass can. It's developed a tolerance to it. In fact, the discovery of the Dugald River can be linked directly to the presence of this grass, because the first person that flew over it in the 1920s spotted this, which was essentially what they thought was a runway. But it's not a runway. This is the surface exposure of the Dugald River deposit. And closer inspection reveals, obviously, that it's the along strike the ore zone. Fortunately, MMG, who are currently mining Dugald River, have kept this area. So it's sort of fenced off. Hopefully they'll keep it for a while, because these copper plants are well worth study, as we'll see. That obviously got me interested in copper grass. Who wouldn't? You're looking for copper around Cloncurry, and if you can spot a little bit of outcrop with some grass growing on it, then you know that there's probably some high metal concentration. Obviously, it doesn't mean that there's a deposit, but it does mean that there's probably going to be something worth looking at. So this particular copper grass is Eriacne mucronata, and common throughout northern Australia. Cattle don't tend to eat it until it's the last resort, which I think is pretty funny. And it has a very distinctive sort of almost wheat-like seed head. So once you get your eye in for it, particularly in the morning and evenings, driving out in the ute across the scrub, you can spot it quite easily. And it's very common. Here's an example of my friend Gavin and I. We were just doing some prospecting and we came across this area, and I was convinced that this was a drill pad that someone had put in, because the lines were so angular, but there was no evidence of drilling. There were no drill on record. This was just where the surface outcrop that contained copper was, and there's the spinifex, and this is all copper grass, and the spinifex can't grow here, so monoculture has taken over. This was a prospect called Green Hills. Funny enough, pretty much all of these rocks were green. So the prospect, obviously called Green Hills, covered in copper grass. I was given a bit of, light to medium natured banter when I went back to the office, clutching clumps of this grass, telling everyone that I'd found something that grows on copper deposits. It wasn't universally accepted at the time, but it was well reported in the 70s and 80s. The Midakudi people know all about it. It's a common thing for them, and certainly the research in recent years has certainly proven that it's a thing. My favorite example of sort of, I don't know, proof that this is a thing is that driving to and from Ernest Henry, the mine, about 35-40k north of Cloncurry, driving to and from there one season, I remember thinking, geez, that's copper grass growing right at the side of the road. Why is that growing at the side of the road there? Because there's no copper deposit there. There's no, no obvious reason why there should be copper grass growing at this particular sorry, just hiding those meeting controls. And basically, long story short, Ernest Henry, which is now owned by Evolution, exports sends their copper concentrate by truck. This is the first corner as you leave that mine, and the road's a little bit bumpy. So any copper dust that's on those trucks as they come out, this would be the place that the copper falls off. And I've actually done an XRF survey there showing that the copper is elevated in that zone where this copper grass is growing. So to me, it's very strong proof that this copper grass is a very opportunistic plant and will grow where there is copper. So pretty cool, I think. Anyway, I could go on about this all day, sorry. Anyway, there are other species of copper plant. This is Bulbostylus barbata, which is a very little one, but it grows very quickly after the rain. So quite often you'll see this sort of growing when other plants haven't quite got round to growing yet, and it dries out nicely, so it's there over a course of a couple of years. Polycarpia glabra, this is the Cloncurry one. It's actually a very interesting plant because this only really grows where there's over 1,000 ppm copper. So if you see this, the chances are the rocks underneath it will be green with copper secondary minerals. It's a very cool plant. In fact, I was doing some prospecting one time in an area where the rocks are all this color. In fact, you can see in this image here, all the sort of, zoom in again, you can see all the sort of green and malachite stained, chrysocolla stained rocks that this is growing on. And one of the prospects that we actually found partly through the presence of this copper bush, we then did follow up soil surveys, and some of the soil had percent levels of copper in, so we drilled it, and that's actually now become, I think it's about 25 million tons of ore in the EVA copper project resource. It was drilled out by the company that had it at the time. I think it's Harmony Gold have got it now, but it was drilled out because that was actually going to be under one of their tailings dams, and the fact that there was 20 odd million tons of extra ore there meant that they shifted those around, which is good, and hopefully those plants will be preserved to some extent as well. They are throughout the Cloncurry district. And there has been a fair bit of research on these, looking for them to be potentially hypoaccumulator plants. There's another plant, just this will be the last plant, sorry, I won't go on about plants the whole time. But they're all linked into it. They're all linked into this sort of development of regolith, development of Gossans, that sort of thing. This is a sort of more of a leguminous shrub. I always find it interesting that around most of Cloncurry, this shrub grows with a sort of purple flower, whereas in the Roseby corridor, it's got an orange flower. And this was tagged as potentially being a hyperaccumulator. Where again there are plenty of known hyperaccumulator plants that rather than exclude the metal, they actually absorb it on purpose. We thought this could be something for copper, in the sense that you could sow this on your waste dumps and extract very low levels of copper through the plant. Didn't work out that way, but the people like Peter Erskine are still researching at University of Queensland looking for copper hyperaccumulators. We know that there are plenty of nickel hyperaccumulators. I forget the name of the plant, but a lot of plants in sort of wet tropical areas will hyperaccumulate nickel so that they can use it essentially as a bug repellent, because they have a lot of sap sucking insects in those parts of the world, and the insects don't like nickel flavored sap. And some of these plants actually have up to % levels of nickel in their sap. So if you can grow these plants on low grade nickel laterite deposits and harvest them, ash them and extract the nickel, then we have a wonderful modern way of actually extracting metal. So I hope that we actually get a bit more into this kind of bio extraction of metal, because the idea of growing plants on our waste dumps and pulling out other metals is pretty awesome, I think. There is an article in the New York Times, if you Google it, about these nickel plants. It's very interesting. And I should just note, geobotany in terms of the species that grow in certain places is different to biogeochemistry. So we actually find if you analyze copper grass, it actually has lower copper in it than the regular grass growing next to it, because it excludes the copper. So it's more that their presence is just something to take note of. An example would be here, doing some mapping. Back in the day, you're walking through the turpentine scrub when it's all sticky, and you get to an area that's a clearing, and there's copper. This is area can remove big copper grass growing, and then this little copper grass, Buloides barbata, growing as well. So immediately you know that you should probably take a closer look at this. Again, it doesn't mean there's a deposit there, but it means that the plants know something that you can observe from them. And I think plants are pretty clever in that sense. So and every environment has their own indicator species. So getting to know them and learning to spot them is pretty handy. And I always make a layer in my maps of it's looking a bit old now, this one, but I always make a layer in my maps for the plants, because spinifex in this example was growing along the edge where there was a silicified fault. Copper grass was growing along this fault that had copper leaking up it, and we had gidgee trees which have very deep roots growing along a couple of big structures that were full of magnetite. So it is quite handy, I find. And of course, it's not just limited to Cloncurry. When we take the NExUS group around South Australia, up at Wallaroo and Moonta, we find heaps of polycarpia growing around the old mine sites. It dries out nicely. It's like a nice dried flower when it's sort of out of season or dead, but it is very bushy when it's around. I still haven't quite worked out why it grows along the edge of this particular field. Possibly because they add fertilizer here that dilutes the copper, or perhaps the puddles from the waste dumps just here mingle here. But anyway, you see it all over the place, so it's always worth keeping an eye out for. And apparently in the Zambian copper belt in Africa, there's books on it. There's hundreds of species in the African copper belt of copper flowers, and often they were used back in the day to actually discover the copper systems. Although many of them apparently have been the areas have been mined so much now that the plants have actually gone extinct, apparently. Anyway, that's like a little introduction to what sort of got me into like this sort of prospecting aspect side of things. But looking at what these plants are growing on, looking at the surface indicators of mineralization these plants that are telling you about, really comes down to sort of gossans and secondary minerals. So a gossan is essentially a weathered outcropping area of mineralized rock. Any host rock can form a gossan, and it's really just a term that refers to the fact that most of the ingredients of the rock have sort of been leached down. Gossans are generally composed of limonitic material, and we'll look at what limonite is in a moment, sort of iron-rich materials, sort of hydrated iron-rich materials, and silica. It's sort of a red crusty stuff really, but there are a lot of red crusty things in Australia, so we'll have a little closer look. And gossans tend to form a stylized profile like this, with the gossan at the top, which is the oxidized leached zone, an actual leach zone where the The acid formed by the weathering of sulfides has come down and actually removed a lot of material. And then we have this sort of variable water table and oxide zone where minerals like the sort of the malachites can reprecipitate. And then we get below that into an enrichment zone, which is a reduced environment. And again, depending on depth, is all going to be down to the water table. You have a different species of minerals forming there. And then we get down to our primary mineralization. So what's happening up here is an evidence of what's happening down here. And when you're prospecting, understanding the relative location of these different features in the weathered zone of an ore deposit will really help you to get an idea of where you are in the system, what's happening to it, and a lot of the textural retentivity of these systems is actually very interesting as well. Retentivity, don't know if that's a word, but we don't need to remind ourselves of the importance of Gossans for discovering ore deposits, particularly in northwest Queensland, but we could. Great Australia, the first copper mine in Cloncurry, you'd say probably the first copper mine to really unlock the potential of the whole Mount Isa district, discovered in 1867 by Ernest Henry, who was up pretty much the first Westerner to be up there. And Great Australia was a great big gossanous mound of hematitic, girthite, limonitic material with all sorts of copper through it that he discovered fairly obviously. The story goes that prospectors would show local Midakudi people lumps of malachite and ask, take us to this, take us to where Big Man Copper sat down. And that's how a lot of the discoveries were made up through that area with the help of local Midakudi people. Obviously, these sorts of rocks are quite obvious, and there are many stories in the Midakudi culture around the origin of those. Mount Isa was also discovered by someone recognizing the Gossan. Of course, Mount Isa is more of a lead zinc deposit. At surface, the copper's deeper, and it was discovered by John Campbell Miles and in 1923 because he'd actually already worked in Broken Hill, so he knew what the characteristics of a lead zinc Gossan were. They're much darker. They don't have these bright greens and blues, and they're generally sort of whitish or maybe yellowish kind of minerals, sometimes pale blue. We'll look at those later if we have time. But he recognized them because he'd seen them before. And people have been walking past Mount Isa for 30, 40 years before anyone actually bothered to stop and look at it properly, because they'd all been looking for these. They'd all been looking for secondary minerals of the copper variety and not secondary minerals of the lead zinc variety. So very important to know. This is an example of what some of the stuff around Mount Isa look like. The red is limonite, but it's this white material that's all massive cerussite, which is a sort of lead carbonate. So I just have a cough from it. Another case study that I'll just throw in briefly, MacArthur River, also called Here's Your Chance. It's one of the world's largest zinc, lead, silver deposits. And the story that I recount is the version that I've heard from Roger Taylor a number of times, that the Mount Isa Mines geologists were visiting this area that became known as Here's Your Chance back in the 1950s. The local grazier had noticed that there was this big outcrop of weathered looking rocks, and as you note as well, there's no trees growing on it because the soil would be, or the regolith would be, highly enriched in lead, zinc and silver, I suppose, although silver's not fairly inert. But it was a Gossan, very much so. It's limonitic material, the remnants of the weathering of sulfides such as pyrite that's leached a lot of material down, leaving you with essentially iron and silica. And there was this white mineral throughout it. I think this is a toy that someone used as a scale, because I've never quite understood why that's in the photograph. But these are photographs from not 1955, but a bit later on. But this white mineral wasn't necessarily recognized at the time. And the story goes that the initial prospectors took lumps of it back to Brisbane, had it on their desk and waited for the geochemical assays to come back. And then a prospector came in and said, "Oh, that's a nice bit of hemimorphite. Where do you get that?" And hemimorphite obviously being a zinc silicate mineral, which is a very pretty mineral. If you ever get a chance to have a look at a sample of it, it's quite nice. You don't see too many zinc secondary minerals, but that one and smithsonite are about the main ones. So we'll look at that a bit later if we get a chance. So yeah, the major discovery at MacArthur River, and here's your chance. Over 100 million tons at crazy grades of lead and zinc. Very, very, very fine grained sphalerite and galena though. So it actually had quite a lot of issues with the technology to even recover the metal from it. So it took many years for that to catch up. But eventually, when they solved those metallurgical issues, it's become a very, very major ore body in that area. And the first image I showed shows that it's gone from being an underground mine to an open pit, and probably got the most regular distribution of ore in any deposit I've ever seen. So, but that's probably another story. I was fortunate a couple of years ago to spend an afternoon with Matt there on the surface by George Fisher and Hilton Mine north of Mount Isa, and we were looking at, again, these limonitic, sort of hematitic, gossany materials, showing preserving the features of the Urquhart Shale and the more silicious areas. Boxworks, which I won't have time to go into today, but these are where you've had pyrite grains weather out, so you leave a sort of almost like a sponge-like impression of the pointed little pyrites in the rock there. Those are very useful to look for if you're looking for gossans. And we just found a nice little lump of what at the time I thought was sericite, but when you actually have a closer look at it, you can see the little radial fan-like crystals, and it's hemimorphite. But again, still sitting on the surface, and it's over a zinc mine, so not surprising, really. So what is a gossan? In terms of the definition, it's a moderately heavy accumulation of limonitic material derived from in the main from massive sulfide ore. So really, we keep acid in glass bottles, which are made of silica, and really the iron and the silica are about the only things that the acid won't dissolve. And I put one equation in there, but basically you take pyrite, oxygen, and water, and you end up with sulfuric acid plus some other things. So plenty of opportunity in weathering a sulfide ore body to create acid. And of course, pyrite is by far the most common mineral in a lot of these systems. So exposure of an acid forming mineral forms acid, leaches everything it can leach out, takes it down to the water table where often that's precipitated. So you're going to be finding your malachites and your other minerals sort of down here. And we have this leach zone that we'll look at in a few moments. I guess, yeah, depending on where in the world you are, gossans won't look the same everywhere, because you're going to have different presence of bacteria, different EH or electrochemical conditions. So saying it's just acid is a bit of a summary, but if you get into the detail of it, obviously everywhere is going to be slightly different depending on the environment that you're forming it in. Hence, different minerals forming in different locations. A few words on this slide, I won't read them all, but essentially it says that when you weather an ore system at surface, you're going to get different outputs based on the inputs from the natural environment. The original mineral assemblage, the solubility, the acidity or the alkalinity of the groundwaters, temperature, bacteria, uplift rates. There's a whole range of things, but can be summarized as, if you put a piece of chalcopyrite on the surface in Sweden, it would probably weather a little bit different to how if you put it on the surface south of Cloncurry, based on the aridity, based on all those factors. Probably going to end up with most of the same minerals, but they will take a different amount of time to form. I keep meaning to put a bit of chalcopyrite outside my office window and watching to see how long it takes to weather to malachite. In fact, I do have some. The chalcopyrite has tarnished in about 2 years. Looks a little bit like bornite, but that's another story. But I'll let you know when I get malachite forming outside my window. I reckon 3 or 4 years is probably about right. Anyways, I hope this is all right. If anyone does have any questions, please pop them in the chat, and Anna or Leah can interrupt me. I am prone to prattle on at this sort of topic because I quite like it. Quite a lot of work's been done regarding different gossans, but of course they're going to be different in different areas. And depending on the migration of that water table over various times, you can actually, of course, have your oxide zone come back up. And then you end up with, you actually end up with, malachite and other secondary minerals overprinting gossans, which may or may not get back into solution and go back down again over time, depending on that water table movement. Actually, I may just pause there for a moment. Anna, are there any questions? Has anyone? I did just notice when something popped up that that there are a few things in the chat. Any particular questions that have popped up?
Yeah, we're getting some good comments. So no questions as such.
Is it pointing out that I'm completely wrong about everything?
No, everyone's just
Excellent,
giving their
excellent.
own little stories about copper.
Oh, good.
Yeah. There's some links here. Owen's discussed how crassicol is a great copper secondary mineral, even though it's not very well structurally characterized. So obviously, I think there was a mention earlier on about it. There's a Owen's also popped in an article about in Indonesia about the was it the Canandra plant, Canandra plant? It's a nickel hyperaccumulator that they've used to mine metals, I guess, like cleaning up. There's been a fire alarm. Hope you're back soon, Vanessa. And then it's a discussion about how copper is often used for the soils. So that's probably why you see that the copper
Excellent.
plants at the side of the roads. But I think everyone's just sitting back and enjoying the show. It's great.
Excellent, cool. I shall carry on then. Thanks for that, Anna.
Yeah, that's
Good.
okay.
I needed a bit of a pause. So yeah, no, that's all good. So yeah, basically the zones of these Gossans can be, your Gossan and your leached zone. Less you may get some oxides precipitating back in here, but the main zone should be in that sort of oxide zone. And then, of course, once you get under the water table in a reduced environment, you're going to have a different species of minerals because that's going to be more reduced. So you're likely to end up with your more sulfide minerals again, but secondary sulfides such as chalcocite and other ones, which we'll have a look at a bit later if we have time. And again, I'm sticking mainly to copper because this is my experience really, and they're prettier. They're very pretty minerals. So what do Gossans look like in the field? These are images from Roger Taylor's book on Gossans and leach cappings. And this is a nice one in Mexico, copper, silver, gold, lead, zinc prospect. And you can see obviously here, limonitic material, sort of red material, looks a bit lumpy, could be a breccia. You can see some remnant layering there perhaps. Also you've got these patches, slightly irregular patches of very white material. So there's your sort of leached zone. So if you're an explorer and you found something like this, particularly among other rocks, you'd be very interested of that. So and also relatively limited size. So that's immediately telling you it could be a more limited sort of vein or sort of high sulfidation system. This is probably my favorite, again from Mexico, from Roger's book. And a very conspicuous red gossanous material, again with these white patches. It's not random, that's the leached zone. Two things I like about this. One, there's not much vegetation except this particular kind of slightly buff coloured grass or buffy green kind of colour grass, which may well have a tolerance to high metals. And the other thing I really like about this is if you extend your view over to the far side, there's another one over there. Which says to me what's happening in this valley. So again, simple recognition that these, highly oxidized sort of, iron-rich leached zones are probably telling you something about the rocks that had them in before. It's really prospecting 101. So I do like the vegetation anomaly in this one. So what is limonite? Like limonite, there is no specific mineral called limonite. Limonite is a bucket term for a variable mixture of hematite, goethite, both sort of iron oxides, with a variable amount of jarosite, gypsum, and allanite. So I do know some people who carry around these sort of color wheels with 100% hematite, or sorry, 100% goethite to 100% hematite, or goethite to jarosite. Goethite tends to be that really vibrant orange. Hematite tends to be that sort of brick red, and jarosite can be quite bright yellow from times. Here's an example of a piece, and this is pretty typical of pretty much any rock that you pick up near a mineralized system in Queensland. Things to note here are the fact it's mainly composed of iron oxides and silica. And probably this bit here, you see the top of it, the bit that was exposed to sun has gone back to hematite, because goethite's a hydrated iron oxide. And if you bake that in the sun for 200 years or 1,000 years or however long that's been sitting under the Queensland sun, that's going to get rid of any moisture that there may be. So that's quite often you see this kind of desert rind in places, which can often be full of manganese as well, which we'll look at in a moment. But you've got this sort of limonitic material. Obviously this has been probably silicified, and again you have to have quite specific regolith conditions, or sorry, environmental conditions, to free up silica to actually get that almost like a silcrete forming. But you can see here is quite a distinctive enrichment in silica through this part. Obviously probably the silica has come after that hematite, so it's kind of almost the hematite's been silicified in this case, perhaps. I can't quite remember exactly the sample, but of note is that there's no malachite in here anymore. Although I think there might be a tiny bit there. Most of any sort of copper oxides or things would have gone down in the water table and be precipitated lower down. this is again from Lorena. I pop this in as a little bit of an aside because it's the role of bacteria and something that you don't tend to think about a huge amount. Well, I didn't. This was sampling with a guy called Gordon Southam, professor at UQ. He's a geomicrobiologist, so he studies bacteria and their interaction with sulfide minerals and things like that. Gordon's been down an awful lot of mines around the world sampling the kind of red sludgy stuff that drips off the side of the wall, because often that is full of bacteria. He's here at Lorena sampling this vein, and it is a vein, but you can't see it because it's covered in sludgy. It was damp, it was smelly, it smelt of sulfur. It was really quite active, live sort of limonite forming here. And he took a few samples. Now, the next images are not from this sample, but they are relevant in that this is a close-up of a grain of pyrite. You can see the sort of edge of the grain there of a pyrite crystal, and it's covered in this kind of crusty material. This is under SEM imaging. Zoom into a bit arbitrarily there, and the crust starts to look a little bit fibrous, and you think, well, you see the scale we're on here, 2 microns, so it's pretty small, crusty sort of material. And then you zoom in again to the zone here with these little oblong things, and those are actually individual bacteria, and these are actually forming jarosite and schwartmanite, which are iron oxysulfate minerals, from the process of them eating the sulfur from they're surviving on the sulfate reducing bacteria. So they're eating the sulfur of the pyrite and they're producing these iron minerals as a waste product, shall we say. And I think it's fascinating. Gordon reckons that the presence of bacteria are essential in forming these reduced iron compounds that we find in Gossans all the time. And over a glass of wine, he told me once that he reckons the presence of bacteria can speed up weathering of sulfide minerals by 1,000,000%. And I believe him because I've been to places where you have pyrite sitting on surface, perfect cubes, doesn't look weathered at all, and you go 10 meters down the road and it's absolute sludge. And I would say that the environmental conditions are no different in that case, but it's the presence of bacteria here and not there that lead to this weathering. And I see it all the time. I don't know a huge amount about bacteria. I know nothing about bacteria apart from these images, but I think it is pretty cool that when we see these sort of limonite forming in these sort of rivulets of iron-rich material in mines underground, that bacteria will be having a large role to play in the formation of that. It's not simply just oxidation, but the bacteria are getting into it as well. So I think that's pretty cool. Bit of an aside, but something I like to mention because I think it's interesting. Manganese oxide is something we often see, these black crusts and these dendrites. We often see those. I've lost track of the number of times I've seen people posting pictures of these on even things like LinkedIn, where they're calling them fossilized plants and things. We've all been there. But manganese oxide is a bit of a bucket term for the 2 main manganese oxides, pyrolusite and manganite, which, speaking to Roger Taylor about this, they are so minute in terms of their crystals. You really need a high-powered SEM just to even pick them apart, and there's not much point because they'll be intergrown quite often. So manganese oxide is, again, a bit of a bucket term for these things. And manganese is really interesting when it comes to scavenging minerals. Being a reductant, it will actually sort of absorb, almost like a sponge, ions of other elements. So, often people will hack this crust off to actually sample that to see if that's sort of scavenged free ions from nearby. Again, my chemistry isn't amazing on that, but I know that it's something that if you see plenty of, it's definitely worth sampling. And we'll tend to find the manganese is pretty unreactive well, so we'll see that up in this sort of Gossans zone too. And here's an example from Mount Isa. Of course, if you have a system that has more manganese in it, like a lead zinc system or a system hosted in shales, you will often see a lot more manganese hanging around. So this sort of black material would be that. And this is an example from Mount Isa. And note how, even though the rock is heavily weathered, you'd say this is a Gossan. It's got high amounts of limonitic material, varying amounts of hematite, reflecting the composition of the clasts, perhaps, and the fact that texturally, the breccia that this rock is or was before it got weathered is very well preserved as well. Often these surface weathering processes preserve the texture of the rock very, very well, but we often don't look because it just looks like a bit of cruddy red stuff, and we just toss that away looking for something more interesting. But the textural retentivity of these processes is actually excellent. So once you know what to look for, you can find all sorts of things within these gossinous weathered pieces of rock. And this is another sort of botryoidal manganese mineral, but this one, I believe, from a place called Bernborough, which is just south of Mount Isa, literally like a few hundred meters south of Mount Isa mine, is one of these really random minerals that there are two places in the world it's found. One is at Janshu, hence the name Janshuite, and the other is at Mount Isa. So again, these minerals are all quite interesting, and obviously it's composed of manganese and magnesium. There's a lot of dolomite up at Mount Isa, so of course you're going to get quite a lot of magnesium hanging around as well. So in our exposed domain of Gossans and ironstones, let's bring it through to sort of Australia. How do we know that the red material that we are sampling in the desert is a Gossan, or how do we know whether it's an ironstone? Or this is a cartoon that I've redrawn. I apologize for not leaving the original reference in there. But you know, we have lateritic ironstones, we have translocated laterites, we have actual Gossans, we have you know, ironstones, we have sort of fault ironstones. There's a lot of different ways you can form this kind of iron-rich material. As Nick Tate says, if it's brown, bag it, you know, sample it anyway. And there are examples. This case study would be from Mount Isa, where a fairly big study was done on all the different gossinous outcrops, all the sort of red, rusty looking outcrops, and it was fairly obvious which ones had an origin that was related to hydrothermal mineralization rather than literally an ironstone that's weathered in the desert. And that work is available on the Queensland Geological Survey website, and I'll be able to provide a link for that at some point in the future. But essentially, they had very low levels of lead, zinc, and silver and copper in them. That was the main distinction. So yeah, there's all sorts of things that you can spot in the field, and if you are fairly careful with your geochemical sampling, you should be able to spot whether it is an actual Gossan or not. But I haven't really got time to get into any more detail on that here. But I should provide a reference. I'll just pause there to give a little shout out to the course happening on Monday that I know a few of you in attendance are signed up for. So I hope to join you on Monday and you don't get too bored hearing the coppergrass story again. Surely you'll never get bored of that story. But yeah, so Dr. Roger Taylor has got over 60 years of experience exploring for these sorts of things and has literally written the book on them. So Roger will be taking us through his examples and I'll be chipping in with a few of mine. If anyone's interested, there's still time to register. So please use that QR code up in the top corner. And that will give you a link to the registration, and more than happy for anyone attending today to sign up for the AIG reduced rate. That would be absolutely fine. Carry on for a little bit, Anna. This is one of the places I probably could stop, but we'll just keep going for another 5 or 10 minutes just to go through the leach zone and maybe have a look at the oxide zone as well. So we've looked at the cause of what's forming the acid with this sort of essentially weathering of sulfides and weathering of pyrite in particular in many systems. And you know, Gossans are not limited to Australia. Obviously, they're all over the world. This is a great example from Escondida Norte, which is one of the world's biggest porphyry deposits. We can see this lovely sort of gossinous, you know, not so much limonitic here, but certainly hematitic sort of reddish material, and grading down into this sort of like extended leach zone, which looks particularly green here. So I'd imagine that the water table has changed around a bit, and that this is probably secondary precipitation of things like malachite, possibly chrysocolla as well. So there's a lovely example there of this sort of zone through this Gossan and leach zone, and potentially you know, mobilized oxide zone. This is apparently what it looked like before they mined it in another part of the system. It looks like the surface of the moon, but this is essentially the Gossan here would have been weathered off, and we're now looking at the exposed leach zone. Of course, these systems forming in Australia, where there's very low rates of erosion in most areas, very ancient crust or ancient exposed surface. Obviously in the Andes, with them going up however many millimeters per year, you're actually going to get quite a lot of throughput. So if these things form, they might get weathered off Hence places, you know, some of these high altitude zones might actually have fresh sulfide because they've actually not had the time for the Gossan to form, or if the Gossan did form, it's been weathered off the top. That's a close-up of some of these sort of leached rocks. They're essentially vuggy quartz. So everything's gone except for the quartz in these samples, and the vugs are obviously where other minerals were. But in reality, most of these things look a bit like this. This is sort of, you know, it's always going to be a bit of a mix. You've got these sort of almost boxworks where there may have been sulfides. You've got leach zones, and you've got the sort of like zones with variable amounts of limenitic material. So we'll nip down quickly into the oxide zone and skip through a few minerals. Again, could spend a bit more time on this, but really a bit of a cover all everything today. Obviously, we talk to things about hypergene to supergene. Hypergene meaning under the ground, supergene meaning above the ground. And it's pretty handy for explorers and for miners because chalcopyrite is around 35% copper naturally, and malachite's nearly 60. So nature's doing your concentration for you. Things like cuprite can be upwards of 70%. So, you know, you can actually form very, very high grade, very, very high value deposits from this supergene weathering process. I've heard of, you know, large amounts of the African copper belt. There's huge amounts of malachite that can be mined, obviously, or carved into trinkets. And I did hear once there was a mine that was actually mining tenorite, a big blanket of tenorite that was very high grade as well. But we'll look at that shortly. Example of our chrysocolla here, silicate mineral, not normally used as an ore because it takes too much acid or too much processing to get the copper away from the silica bond. But again, pretty, and certainly a mineral that probably deserves a bit more study. I've given you the example of our multi-commodity indicator here of multiple copper and arsenic minerals, and you probably don't want to lick that one, but it's pretty all the same. So look, skip through a few common oxide minerals. I'm sure you all know these. I'm not teaching you anything, but I just like putting pictures of rocks up. This is an interesting chart, again, from Roger's book, that shows how the variation in pH and EH will affect which mineral species you have growing. I summarize it by going wet, dry. So up the top here, you'll get your sort of your malachites, your tenorites, your atacamites, and down the bottom there, you'll get your cuprites, chalcosites, and covalites, which we'll look at. That's massively oversimplifying, but obviously there's quite a few inputs into that. Malachite we all love as an explorer. Nothing better than cracking open a rock and finding a bit of malachite. Been valued as a gemstone since antiquity, and for the explorer is highly valued. And obviously it often occurs with azurite. It's actually, I believe, azurite and malachite essentially got the same chemical formula, but azurite's got a bit more water in it. So it's why you commonly see malachite and azurite together, because they're essentially the same thing, just one's dried out a bit more or had less water around when they formed, I believe. Please put in the comments if any of this is wrong, because I'm not a gemologist. I just picked up this information as I go, really. Azurite's another good one. You often see it pseudomorphed. I've seen azurite sort of blade pseudomorphed into malachite, pseudomorphed into chrysocolla in the same location. You also get pseudo-malachite at some of these locations, which is a phosphate-rich malachite, so a bit of a sort of darker green. Atacamite, brocanthite, and antlerite are all very nice minerals, rare, but the one to note here probably is atacamite, which is a chloride mineral. So you get that in salty environments, named after the Atacama Desert. But some of the best examples in the world come from a place called New Cornwall in Cadina, about 2 hours drive north of Adelaide. And there's a crystal about several inches long in the New York Museum, I believe, that came from New Cornwall mine. And we go there every year with NExUS, and every year we find these beautiful samples of atacamite. And again, it is a pretty mineral, and it's very much a copper mineral, but what it's telling you is that the groundwater is really salty because you have salt in it. So fairly obvious, really. I think brocanthite tends to be these slightly stumpier crystals, and I do have a piece of antlerite, but it's not the most beautiful. I think that's probably antlerite up there, a bit more fibrous. Again, the trick with atacamite is that it's very gemmy. If you get it in the light, sometimes you say, "Oh, are those malachite needles, or is it a acicular malachite, or is it atacamite?" And atacamite really has a very bright reflection to it. It's very gem looking, so it's very nice. Chrysocolla, again, rarely used as ore, hydromorphic mineral. It will absorb water if you put it on. I'm pretty sure that if it doesn't really form in wet environments, it's much more of a dry climate mineral, much like turquoise. But turquoise is a phosphate, and so it's much harder, which is why turquoise gets used in jewelry in antiquity in Persia and Southwest America. And I think that's fantastic because it's a very beautiful mineral, but it's, chrysocolla doesn't, well, it does polish, but chrysocolla is a bit more brittle, whereas turquoise is obviously harder because of its composition. And of course, it only forms in very dry environments, hence it being present in places like Persia and Southwest, where it's become adopted into the culture, which I think is all a nice kind of holistic geoscience story as we go. Cuprite is probably my favorite copper mineral, has a metal content of up to 89% by weight. If you Google cuprite, you end up with seeing these beautiful red cubes, but in reality, you normally see it as this kind of fine grained mass of sort of red silver. If you get the hand lens on it, it often is red, but when you look at it, it can be kind of silver. I had bits of cuprite on my shelf, which I thought were just hematite for years because it's got a similar coloured streak, that kind of copper coloured streak. But it's a great mineral, and that's the one that they used to like up in places like Cloncurry back in the 19th century, because you could, once you've got chipped off the waste rock and you just end up with, masses of cuprite, you end up with a very valuable ore. So that's a good one to find. Tenorite, often mistaken for manganese oxide, but is one of my favorite minerals. Often, if you see like the image here, if you see, this sort of black material with malachite and azurite on it, you might just say, oh, well, it's just manganese oxide. But then the question is, well, we're in a copper play, so there's obviously copper here, so that's almost certainly going to be tenorite. So when you see some of these black, and actually I was in Southwest United States last year in Nevada, and there was a mineral there that they referred to as copper wad, which is a local name for this material, which is essentially a mixture of tenorite and a few other sort of copper oxides mixed in. So often as a sort of sooty powder, you can scrape it off. It's got no strength to it at all. It's quite powdery, but it's a very interesting one to bear in mind when you're in copper systems. And again, because of the variation, they're only a couple of oxygen atoms apart. Often you get cuprite, tenorite, malachite, all coexisting together, again, based on that precipitation and reprecipitation in the groundwater. So it's very common to have an image like here in Roger's book, this sort of reddish fine-grained cuprite rimmed by sort of malachite, possibly with this little dark band of tenorite around it as well. So again, just worth having a look. I've got samples on my shelf that I've looked at multiple times over the years and turned them around and say, oh my goodness, I never even noticed that there was, conochalcite sitting on this rock. So it's always worth having a look. Native copper does happen. There aren't many papers on the formation of native copper, certainly in the crustal environment or on the surface environment. You can form it comfortably in hydrothermal systems. There's famous deposits, I think, in Michigan in the United States, where you have this sort of native copper filling vugs in volcanic rocks. But certainly more of a curiosity, but there are examples where it's been quite valuable. It's one of the native elements, obviously, copper, and it has a whole range of different forms from these sort of almost sort of tetrahedral kind of crystals to these sort of massive botryoidal masses. That's a 3-ton piece that my friend Con has in his back garden in Mount Isa. Nobody wants it in mining because you have to process it differently, and these might often form in fractures and things with water, copper that's got into the water table. But that's another story, really. There's one example called Rocklands around Cloncurry. It's a mine that's got, you could give a whole seminar just on the ups and downs of that particular deposit, but they were pulling out some massive, beautiful pieces. Well, that's a massive piece of native copper. Obviously, they were drilling through native copper, and it's not pretty tricky to drill RC through native copper. Apparently, they were pulling the RC hammers out, and it just had plates of copper stuck on the front with all the bits. It's beautiful samples that did end up on eBay when a couple of people who worked there decided to put a few bits in their pocket. Terrible. But they also, this is a bit of a tragedy story, but they used to advertise back in the day, about 10 years ago, they're advertising their direct shipping ore that they were going to send straight to China. And so they literally had, I think, 12 or 15 small sea containers full of native copper that they'd pulled up when they were pre-stripping, and they had people employed literally to knock the dirt off it and chuck it in the shipping containers. And what happened to that is a whole other story in itself, but nobody ever got paid for it. That was a big problem. Cool. We'll just skip through the last couple of minerals here, and then I think we'll call it a day. So getting down through that oxide zone, keeping in the copper system, we're getting into the enrichment zone, so reduced environment underneath or around the water table. And these chalcocite blankets can be, chalcocite is one of the main minerals, can be very important in the financial evolution of a mine, because obviously if you're going down through your Gossan and you've gone through your oxide zone, which often you won't process because you need a special silex or you need a special acid plant to actually process that kind of oxide material. Once you get down into these sulfides again, you've actually got a very high grade material there that can make or break the finances of the early stages of a mine. In fact, it's the cuprite and the chalcocite that people used to literally hand chip and put on the backs of camels in Cloncurry, walk the camels 400k up to Corumba, put it on a ship, send that ship to England for smelting, and it would still make money. So that's how good a grade we have for this material. Chalcocite is one of my other favorite minerals. Looks a bit grey and innocuous mostly, but when you scratch it fresh, you actually get this wonderful kind of shiny surface. And there are a few wonderful examples of crystals from the Mammoth mine in north of Mount Isa there. And again, it's a 66% metal content, 8% by weight, very good ore. And not to be mistaken with covellite, which is another copper sulfide mineral. Rare to find this in a sort of ore accumulation. It tends to be small platy crystals, and has a very similar color to bornite when you actually look at it. And I've seen a few press releases from junior companies in the last few years saying they've got bornite at surface. It's like, well, it's probably covellite, to be fair, because it does look the same, but it is definitely softer and has a lovely color to it. I think well, I can certainly leave it there, Anna, because there's probably another 5 or 6 slides on lead zinc minerals, but I'm not sure how much more you want, how bored people are getting in their Thursday lunchtimes.
Not bored.
Not bored.
Excellent. Right. I'll finish off then, just with and this is a fairly short bit, but the common lead zinc minerals. These are the ones that you definitely don't want to lick. Cerussite is a copper carbonate, and it's forms these classic matchsticks that can be clear, but generally this white material, very dense, so hard to mistake for anything else, very soft as well. Often coexists. A lot of these lead zinc ones tend to grow together, so having individual examples can be a bit tricky. Broken Hill is obviously the classic place where most people have got their samples from around the world for this sort of thing. Anglicite, I only have one example of this, and you often get a little bit of anglicite in with cerussite, but it can be a range of colours. I don't know too much about anglicite. I haven't really found it myself. Pyromorphite is an interesting one. Pyromorphite has these almost tabular hexagonal crystals, and in Mount Isa, this yellow is from Mount Isa, but you can get sort of green pyromorphite, which apparently is from a more phosphate end member. So there's a bit of phosphate in it, and lead chloride mineral with a bit of plus or minus a bit of phosphate, and will lead to slightly different variations in color. And I even have some brown pyromorphite from Broken Hill as well. So sometimes when you're getting into these lead zinc ones, they're a little bit misunderstood and they're a little bit hard to gauge because the colors will vary a little bit. But you can still find this on the surface in some parts of the Mount Isa mine lease. Smithsonite, as Roger Taylor would say, there's very little study into the zinc secondary minerals. Smithsonite is the main one that you will see. Again, it was fairly common. I think they mined it at Broken Hill for a time, and it's very pretty, very botryoidal, clear, can be transparent, greenish, tends to be this blue is fairly typical, but it's that botryoidal form that's fairly common. And then, of course, hemimorphite that we've seen, which has this classic sort of fan-like, relatively hard compared to the other ones, and a lovely fan-like habit. So yeah, last 2 slides is basically, we've talked about over the last 10, 15 years, the importance of exploration through cover, and that we're not going to find another tier 1 at surface. But could we? Could we find, are there still unrecognized ore deposits exposed at the surface? And I think there probably are. Every year you hear about someone drilling under a Gossan. Dreadnought Resources over in WA have been finding lots of Gossans up in the northern part of WA and up here, where people just haven't looked, or they've walked across them and haven't really been looking for base metals. They've been looking for gold, for example. So I think there's very good potential in some of these more remote parts of Australia that we will probably stumble across Gossans that deserve a few drill holes. So yeah, in terms of the exploration process, obviously we have many methods that we have, but geological methods are still very good. And are there still unrecognized ore deposits exposed at the surface that we can help to assess based on identification of Gossans and secondary minerals? Well, I reckon yes. I've worked with people that say no, but I think it's fair to say that yes, but we need to be careful about it. So on that, I'll put up the slide for next week's workshop and call it a day. Thank you very much.
Thanks so much, Richard. That was
You're welcome.
an excellent trip through geobotany, like minerals in the regolith, copper, especially copper, lead, zinc. That was great. And then also obviously taking us undercover and seeing what, how that translates. I actually didn't realize that about native copper either. That I've learnt a lot today. That obviously that'd just smush up and just be totally weird. That's pretty interesting.
It's pretty soft.
Yeah, and that's okay. I'd love to hear the story about the direct shippable ore.
Well, if turn the recording off.
Yeah, we'll turn the recording off and we can talk about it. Do we have any questions on the floor? I know there's a few people have stuck around, so thanks everyone. Aditi, you had a question, didn't you? Or a few?
Yeah, I actually have two questions by now. So the first question, I'm audible, right?
Yep.
Yeah. Okay. So the first question was about the some of the textures that I saw. Like they were pretty angular. So the sides were weathered, they were darker, and the clasts of the rocks were pretty angular. So that was very counterintuitive for me. Maybe because I'm from India or something, because I always felt that weathering would reduce the angularity in the clasts, but I see that the surrounding is so weathered and the clasts are very well preserved. So I was just wondering why that is. And
is that specifically, could you say which of the, which is it the image from Mount Isa you're referring to with the manganese, or?
Yes. So there was this
find
dark patches around. It was the slide. Yes, exactly.
That one.
That one. Yeah.
Yeah. So basically those rocks haven't moved. That the image there is of an outcrop of weathered material, and the outcrop, the clasts were breccia fragments with it. They were angular breccia fragments within the rock, and the rock has subsequently just been exposed. So the clasts haven't been affected, just their composition, I guess, has been affected. They haven't moved anywhere. So they were in a breccia like that with probably dolomite around them, as they, so the breccia occurred underground during the mineralization process, and then subsequent weathers just preserved those textures.
Right. So they're being protected by the layer of dolomite around.
Yeah, I guess so. Obviously, if they physically broke out of I guess the breccia was an angular breccia to start with. So yeah, they haven't gone anywhere since then.
And my second question is about, so let's say as a student, like if I want to transition to this domain, if I want to work into like in the field of regolith dominated terrains, what are the hard skills that I would require? I don't know if I am able to explain my question. So
No, no, you go.
So for example, I had done a few courses like geomicrobiology long time back, like 5 years back. I did a small project on weathering, but they were always considered as a side project. Like so today I could finally piece together those things. And I said, oh, okay, this can be applied. So that's the reason why I'm so curious to know about it.
Yeah, look, I think as you say, all of these things that people pick up over the years are different bits of experience. Quite often when you're working in exploration, it's all those things that you can draw on that are valuable. So I wouldn't say there's any geological education that you can have that becomes completely irrelevant when you're exploring, because you never quite know what you're going to be looking for or might turn up. In terms of what do early career people need to be involved, particularly in this kind of prospecting, you probably want to have a good fly tolerance. Good sun hat, You know, being able to drive manual car and change a tire, that's probably quite helpful too. So no, it's a bit hard to say really, but it's really nice when I hear about feedback from previous students or NExUS attendees who are actually getting to go out and do, you know, some of this, actually be out doing field work. And, you know, a lot of people I know in my peer group, you know, really quite excited on LinkedIn when they actually get to go and do some field work for 2 weeks instead of staring at the computer. Am I right, Anna? So yeah, no, actually being able to get out and do this sort of work is a bit of a luxury these days. And you only have to go back 20 or 30 years, and this was what people did day in, day out. So actually boots on the ground exploration is, I wouldn't say a rare thing, but it's, you know, it's particularly with the advent of AI and all the data science around big data sets, actually just going and saying, what mineral have we got here? Why has no one drilled under that Gossan that people were chipping away at in the 1890s? That to me is one of these potential missed opportunities that we could have overlooked something pretty massive.
Right. Thank you so much.
No problem.
Thanks, Richard. And I totally agree. I think there is something to be said, you know, as much as it's pretty tough being an exploration geo out in the field, and especially when you're out there for the first time, you do get a lot of that hands-on skills, especially, you know, a good exploration manager's got you at least mapping a little bit and walking around looking at stuff. So that is how you get your eye in. Definitely. Yeah, thanks, Aditi. Great questions. Do we have any other questions out in there in the audience? I know Georgina's asked, can you spot the difference in colour of the grasses and satellite imagery? I was thinking that too. You know, there's a lot of people doing some good work with spectral imaging and satellite imagery, looking for different types of plant populations.
Yeah, as far as I'm aware, because someone did ask this a few years ago, I think someone did look into it, and there isn't enough difference between the copper grasses and regular grass in terms of their spectral signature. And often the copper grasses are quite relatively small populations within a larger area. However, certainly from interpretation of satellite photos and aerial photography, once you get your eye in for an area, say a tenement scale area, you can definitely get a fair way. And then it's just a case of planning your drive in past it to check it out. And certainly in the Roseby corridor, for example, once we got our eye in for it, we definitely identified. Again, it probably wouldn't be. Again, it's not really spectral, but if you just muck around with the RGB on regular photos and boost colors, and you can normally, once you know that there's an area of it, you can often pick out other areas with similarity or looking for similar patterns. But in terms of a specific signature, I don't believe they have one. But again, once you've also blanketed the whole area in surface geochemistry, they stand out as being the areas with high copper. So like it's so that's always been quite useful time.
Yeah, it's great. Thanks, Richard. Okay, I reckon that's probably it. I think if anyone wants to know anything else, we're going to come to your course, don't we? I feel like I need to take the day off and come to your course now.
Well,
great.
I'll send you the link, Anna, no problem.
Yeah, no, I'd love to. It'd be really fun. I think it'd be. All right, yes, okay, yeah. Sorry, kids here. School holidays. Thank you so much, Richard, for coming today and presenting this excellent talk. I think we've really enjoyed it. I think a lot of people, have learned something new. I definitely have. I've got a lot of just background reading up to do. It definitely is going to help me inform some of the work I've been doing, just even with copper minerals and up at Kapunda. So it's definitely that's actually been a good backstory. I've quite enjoyed it. So thank you.
Excellent. No problem.
Oh, my kids. Right, so I'm going to wrap it up. Next ARGA webinar will be announced once we lock someone in. We do have just at ARGA News, we have the Australian Earth Sciences convention coming up next year. We're going to have an ARGA symposium, which is going to be really great. So if you are doing anything that you think could be fit within our theme of either mineral exploration and regolith and weathered terrains and regolith materials, then or in landscapes environment, please do get in touch with us. We would love to lock you in as a potential abstract. We are also going to have a special edition of the Australian Journal Earth Sciences. We have our editor, guest editor locked in, and if anyone's interested in helping out with that, we'd love that. We would love to have any potential papers, ideas sent to us as well. So do get in touch. We do have a newsletter. If you're not a member already of ARGA, please do join. It's very cheap through GSA. And let us know if you'd like to be on the newsletter list otherwise. All right, that's it.
Cool.
Thanks, Richard.
Excellent.
Really
Thanks
appreciate
very
your
much.
time. Thanks,
See ya.
everyone.
Cheers.
Have a great
Bye-bye.
day.
Thank you, Richard.
No worries. See you. Bye-bye.
Bye. See you.